Welcome to Module 3, Buildings as Cyber-Physical Systems. In this module, we will look at the modern building as a connected system where physical equipment, sensors, controllers, networks, software, data, and people all interact. The key idea is that a digital action can create a physical consequence. That is why building automation must be managed with engineering discipline, not just software convenience. By the end of this module, you will be able to explain why a building is a cyber-physical system. You will identify 6 architectural layers, trace information and control flow, define system boundaries, and explain why data quality is an engineering property. The BAS professional must be able to move between the field device, the controller, the network, the front end, and the people using the system. The word cyber-physical helps us avoid a narrow view. A controller failure is not just an IT issue. A network change is not just a communications issue. A drifting sensor is not only an instrumentation issue. Each event can change a physical process and affect people, equipment, or operations. That is why the BAS manager must understand both sides of the building, the physical side and the digital side. The book organizes the intelligent building stack into 6 layers. Layer 1 is the physical system, Layer 2 is field devices, Layer 3 is controllers and edge logic, Layer 4 is communications, Layer 5 is supervisory and data systems, Layer 6 is business and organizational integration. When troubleshooting, the symptom may appear in one layer while the actual cause lives in another layer. Layer 1 is the physical building: chillers, boilers, pumps, air handling units, terminal equipment, electrical systems, and the building envelope. This layer is governed by thermodynamics, fluid mechanics, heat transfer, electrical principles, equipment limits, and the actual site conditions. Layer 2 is measurement and actuation. If a sensor is in the wrong location, out of calibration, slow to respond, wired incorrectly, or scaled incorrectly, the BAS may respond perfectly to bad information. Layer 3 is where controllers execute local logic. Typical functions include equipment sequences, PID control, interlocks, safeties, scheduling, alarm evaluation, trends, and failure response. A critical idea in the book is that critical control should generally remain local and resilient. Loss of the supervisory server should not automatically disable essential equipment control. During design and troubleshooting, always ask what happens when the network or front end is unavailable. Layer 4 is communications. Networks transport information between devices and systems. They may include Ethernet, fiber, IP addressing, routing, switching, BACnet IP, BACnet MSRTP, Modbus OPC, MQTT, wireless technologies, firewalls, and remote access. Network design affects performance, security, scalability, and fault isolation. This is where BAS and IT must collaborate, because a digital infrastructure problem can become a physical operating problem. Layer 5 is supervisory and data systems. Graphics, alarm consoles, trends, historians, scheduling, reports, analytics, user management, integration services, and engineering tools. This layer supports decisions. It should not become an unnecessary single point of failure for local control. Layer 6 is business integration. At this layer, BAS data connects to work orders, asset planning, energy reporting, compliance, dashboards, identity, cybersecurity operations, budgets, and project governance. A control loop starts with a physical condition. A sensor measures it. The signal reaches a controller. Logic compares the measurement with the intended state. The controller issues a command. An actuator changes the physical process. The sensor measures the result, and the cycle repeats. Supervisory and enterprise systems add context, history, alarms, analysis, and human decisions, but the fundamental loop is still physical. A BAS manager should be able to trace a point upward and downward. Every BAS program needs explicit boundaries. Which systems are directly controlled? Which are monitored only? Which interface is read only? Which system owns the authoritative command? Which system owns the alarm? Which system stores the official history? When boundaries are unclear, you get duplicate alarms, conflicting commands, and gaps in responsibility. Data quality is also an engineering property. Accuracy, completeness, timeliness, consistency, traceability, and context all matter. A value of 72 is not enough information. Humans are part of the system. Operators acknowledge alarms, technicians place equipment in manual. Engineers change logic, vendors access systems remotely, managers approve risk. A design that ignores how people actually work will create workarounds. Cybersecurity is also physical risk management because digital actions can affect physical conditions. Facilities and IT must share responsibility for asset inventory, segmentation, identity, remote access, configuration, logging, backup protection, incident response, and recovery testing. The best practice diagnostic order starts from the physical process and moves upward. Confirm the required operating condition. Observe the actual equipment, verify the measurement independently, check actuator and output behavior, review controller logic and priority, verify communications, review supervisory configuration, validate history and reports, review operator action and recent changes, then confirm the correction under real operating conditions. For the practical assignment, choose one critical point and trace it from physical condition to digital information and back to physical output.